Swayam Prabha. Digital India. Educated India.
But anyway, going back to business, so this is, a little bit of the background that I think is critical to understand fracture mechanics theory and then how also links with phase field. So just to finalize Griffith's part, so basically he came up with this conclusion, but then of course he did experiments, right? So this is the scientific method. We come up with a hypothesis, and then we need to try to test that hypothesis. So he did experiments on glass. Glass is kind of a model material because it's very brittle, and before understanding ductile fracture is even more complicated, so let's try to understand brittle fracture. So the first thing he said is, okay, he said if we he came up with this expression. He said, so if I take this square root of A and put it there, everything here, except for the failure stress, this is the applied stress, this is the crack length, this is the surface energy, and E. So everything is a material property for A and sigma F. So he said, okay, if I take the square root of A here, is this actually a constant? So he did experiments on glass sheets. He introduced a defect. You can take a glass cutter and introduce a small defect, and then introduce defects of different size and see what load they fail. And he obtained this data when he plots these two quantities. So it is indeed a constant. So that was good news for him. Indeed, it seems that things fail following this scaling relationship. So there seems to be a relationship. There seems to be the fact that the crack size governs failure based on this some sort of material property. So that was a good news. Then he wondered whether this constant, of course, was equivalent to these quantities. And from this data that he obtained from this experiment that we did with glass sheets at different crack lengths, he was able to estimate what these constants would look like, except for the A. So this constant would look like. And then he realized, he could obtain basically everything here is known. We know Young's modulus, we know pi, so he could solve for this gamma. And this surface gamma he found to be 1.75 joules per square meter. And he had additional data suggesting that it was roughly on the order of 1 joule per square meter. So this was good news. It seemed that his theory proved to be sensible. And then finally he tried to use his model to predict the strength variation in glass. And for that he tested glass fibers with different diameters. And his model seemed to agree quite well. And his model was also, he could also extrapolate his model to assume that the smallest defect he could have would be on the order of the molecular diameter, and then he will get a theoretical strength of 11 gigapascals, which was not too far away from the theoretical strength for silica glass that we discussed before. So he was quite satisfied with it. This is the birth of fracture mechanics. He came up with a theory that explained the English conundrum. So yes, English said we needed infinite stress. No, stresses might be infinite locally, but for a crack to grow, we need to achieve an energy. This seems to agree with experiment. There's this relationship, the square root of A of crack length, that seems to agree with experimental data. The estimates of surface energy for an ideally brittle material are on the order of the theory. Experiments seem to be in agreement with theory. And finally, we can understand this strength sensitivity of glass and other materials. So this was a good story. And I guess the idea is that, his approach is in good agreement with atomistic theory, and the defects are always present, even if small. So at the end of the day, the summary is that, you have a material property called toughness in units of joules per square meter that defines a material resistant to fracture. The toughness of a material is the energy needed to advance a crack by a unit area in the material. So the toughness measures the resistance of the material to crack growth. We can measure the toughness in the lab. We can just take a sample of material, we cut a crack, and we pull that sample into the crack growth. So we then convert the critical load into toughness. So for a semi-infinite plate, you can find it here. We can, if we measure the critical load, then, this is for a semi-infinite plate, so one will have to do experiment with a very large plate, as Griffith did, relative to the crack size. But, for other materials, we can also come up with expressions like this one. There will be a geometry factor somewhere. And so we can relate the failure strengths to some critical energy. And I think the only thing that goes beyond Griffith is that Griffith was focused on validating his theory. He was looking into metal fatigue, so he was looking at a wide range of materials. But he was validating his theory with glass. Well, in reality, so he could compare surface energies, fracture energies, with theoretical estimates for ideally brittle materials, looking at really atomic separation strength. And some materials are very brittle, like silica glass, and they have toughnesses of a few joules per square meter. But others, like steels, they have very high toughness on the order of 1,000 or even tens of thousands of joules per square meter, which means that the energy required to create unit surfaces, not only the energy required to separate two atoms, but also energy related to plastic work, to dislocations, and other phenomena. And if you think of carbon-reinforced polymer composites, then the energy necessary to grow a crack is not only the energy required to separate two atoms in the matrix, but also break the fibers that are bridging the crack. So there's other things that can come into place. But thermodynamics applies. We all believe in thermodynamics. It's just a matter of whether this GC is a small number or a bigger number. And you can get here the numbers for typical materials. You can see, of course, metals are very ductile, particularly some metals. Steels are quite ductile. Fiber reinforced composites can also be relatively ductile. And then, of course, what are brittles are ceramics, cements, ice, and glass. These are the most brittle materials. But you can see what is quite remarkable is that you span a wide range. So this is a log plot. So you are really spanning a very wide range of values of your toughness. So it's really quite significant what you're spanning around. So just to finalize, when it comes to Griffith's energy balance, what he concluded was that for the crack to grow, something needs to happen. The energy that is made available or released, the energy stored in the material, has to be equal than the surface energy of the new surfaces created. So basically you have two things. You have a fracture driving force, the energy stored in the material that is going to be released. This is described by G, the energy release rate. That is a function of the loading conditions and the sample geometry. So if we go back to this equation here, so you have basically the fracture resistance is GC, and then the rest of the thing depends on the crack size, the material properties, and the, so well, we can group, let's say you can group these two into a material property, and then you have something that depends on the applied load and the crack size. So you have basically a fracture driving force that tells you how much energy is being stored in your material that is going to be released when the crack grows. And that is described by G, the energy release rate. That is a function of the loading conditions and the sample geometry versus a fracture resistance, the energy required to create unit surfaces, which is described by GC, which is the toughness or critical energy release rate, which is a material property. So if this driving force for fracture G is smaller than the fracture energy, then no fracture will happen. If the energy release rate is equal to the fracture energy, then fracture will happen, or larger, of course. And then there's one more concept that you're probably very familiar with, which is the concept of the stress intensity factor. This came by an American, George Irwin, and he basically reformulated Griffith's approach to make it a bit more practical. So he said, this is Griffith's equation. Remember Griffith's equation for the infinite plate. I can group terms here and define something that will be Kc fracture toughness or K stress intensity factor. And that will be the relationship with GC. So basically you're grouping those two material terms. And this will be GC for plane stress, and this will be for plane strain. But the idea is that you have a term K that you can relate to G, or Kc related to GC, and it's basically the same idea. But the reason why this became a more convenient approach, maybe I'll say first, that at the end of the day, basically you end up with the same thing. You have a fracture driving force that is either G, energy release rate, or K, stress intensity factor, which is a function of the sample geometry and the loading conditions. And you have a fracture resistance, a toughness, that is described by GC or by Kc, the critical stress intensity factor, the fracture toughness. That is a material property. And some books use different notation, so I don't know what you saw in your fracture mechanics courses, but I'm going to follow the approach by Ashby's books, where he calls toughness GC and fracture toughness Kc. But at the end of the day, it's the same thing, right? We have a driving force and something that is a resistant to fracture. And whenever one value is equal or larger than this material property, then fracture will happen. But the reason why so you may at this point wonder, okay, why was this man interested in this K? Why we cannot just use the Griffith approach? It's the same thing anyway. And it is true, but there's some convenience related to the use of this stress intensity factor. And this is because Westergaard showed that the stresses ahead of a crack tip scale with this stress intensity factor. So this basically, there's multiple terms. When basically you get a full expression of the stresses ahead of a crack tip. This is, imagine a crack where a polar coordinate system is centered at the crack tip. So you have x and y, but you can also have r and theta. These are the polar coordinate systems. The stress fields look something like this. So it will be the sigma xx, sigma yy, the shear one, xy. So what you see that the first term is basically some sort of something that depends on coordinates, and then some sort of amplitude factor, k. So basically when you go towards 0, when you approach r towards 0, these other second order terms become negligible, and you find out your stresses. This is the stress tensor, or stress matrix. It basically depends on something that depends on theta, and this 2 pi r squared, so this relationship with r, and then the stress intensity factor, an amplitude factor. And the same goes for the displacements. And by the way, you can see here that as r goes towards 0, your stresses become infinite. So similar, this becomes very small, and this becomes gigantic. So similar to what Irwin predicted, Inglis predicted. So all in good agreement with the previous development of fracture mechanics. But the key point is that because this amplitude factor seems to scale stresses and strains ahead of a crack, this means that my stress state ahead of a crack is uniquely characterized by this stress intensity factor. And this is very important because this brings the principle of similitude. This means that if I have a stress field ahead of my crack in do I have a piece of paper that I can break here? Well, anyway, if I have a piece of paper with some sort of defect, well, I don't want to break this, but if I have a piece of paper with a sort of defect, my stress field here will be characterized by a k value, and that k value will be equivalent to that piece of paper being 10 times bigger or 100 times bigger. Or in other words, we can do an experiment in a lab, measure this k value, and that k value will tell me how every crack exposed to that stress behaves, even if that crack is not in that simple sample that we are testing in the lab, but in a much more complicated component like you see here. And this is critical because we need a relationship between k and the applied load. So we can do an experiment in our lab, measure the applied load, like similar to this one, right? We need an expression. Here is a relationship between k and applied load. So I can do an experiment in my lab. This is for a semi-infinite plate. In other places it will be different. I can do an experiment in my lab, determine what is the critical load at which my, let's say, small metallic component fail, take that critical load, convert it into a critical k, and then that critical k will tell me what's going to happen ahead of any other component made of that material. It could be a bridge, it could be any component, as long as we have the same k, basically. So yeah, this is the idea. This is principle of similitude that we can take. It's the same behavior in a test sample in a real component, as long as that k field exists. And this is what engineers make use all the time. So we run, basically because there's a relationship between displacements and k, or stresses and k, we can do finite element simulations of any component. And engineers do stress analysis all the time, so you just need to add a crack now. And based on those stress fields or displacement field, you calculate your stress intensity factor, and that tells you, how likely that crack is going to grow. And you compare that to a critical stress intensity factor that you measure in your lab using a component where the relationship between the applied load and k. So how do you relate the applied load with k? So it's something like this. So the fracture driving force is a function of the applied load, sigma infinite, multiplied by a geometry factor, and then the square root of pi a being the crack length. So of course this you can express it also like this. This is the applied load thickness. Applied stress is always load divided by area. And then this geometry factor, for some very simple geometries we can derive analytically. So you can see here for a thick sheet is 1.12, for a thick sheet with a plane crack is equal to 1, and so on and so forth. And for others more complicated, we use finite element analysis. But the idea is that I know the geometry factor in the component that I'm testing in my lab. It could be a single edge notch tension. I pull, I measure my critical load, I go here, that tells me what is the critical stress intensity factor. Then I go to my engineering component, I do stress analysis, I determine k, and I figure out whether my crack is going to grow or not. That's the idea. And then the fracture toughness is of course related to the toughness of Griffith. So qualitatively the graph follows the similar patterns. But it's good to get a taste for the numbers. It's good to have, I think most fracture mechanics engineers, if you ask them, okay, what is the toughness of a ceramic? They will say between 1 and 5 megapascals a square root meter. What is the toughness of a metal? It could be on the order of 100 or 200 or even more megapascal square root meter, and so on. So it's a good idea to get a taste from the numbers. And now you can see soda glass below 1 megapascal square root meter, most ceramics 5 megapascal square root meter, ductile metals 100, 200, and so on. Okay, so that's for elasticity. Now we can consider also plasticity. And there's two ways engineers will typically consider plasticity in fracture mechanics. One is through this idea of the transition flow size. And I don't know if you've seen this transition flow size, but because it is taught in some fracture mechanics courses, but not in others. Maybe I'll show you later a picture, and then I'll ask to see how many of you have figured that out. So basically, the idea is that engineers can design based on plasticity or fracture. Right? We want to design against failure. My component can fail because it yielded completely. Sometimes people don't care about that. They can live with irreversible deformations. But frequently in many engineering applications, we don't want to live with irreversible deformation. So engineers will say, okay, if we reach this yielding load, then stop things from happening because I don't want this. I want to change my component. I don't want irreversible deformations. I want to make sure that my stresses never exceed my yield stress. So this you know very well. This is a typical uniaxial stress strain curve for a metal. You know that we have this is stress versus strain. You all know this very well, right? You take a bar, you apply a force, you measure displacement, divide the force by area, gives you stress, divide displacement by changing length over original length, gives you strain. And you have first an elastic behavior. So at the beginning you have this kind of proportional relationship between stress and strain, Hooke's law. Eventually you get your yield point, irreversible plasticity, irreversible deformations start to happen, plasticity, and then eventually you get failure. So that is one approach. This is 1D, of course. In 3D you need to come up with an effective stress, so you need to go from the stress matrix or stress tensor to a one scalar value. So you apply von Mises, for example, or Tresca, or any other yielding criteria, and then you make sure that as an engineer, your von Mises stress is never larger than the yield stress. That's one approach. The other approach is that recognize that our structural component has defects, and it's a fracture mechanics design, basically, right? You say, I not only care about the stress state, I also care about my crack size. And with my stress state and my crack size, I come up with a K, a driving force of fracture, or G, and then I compare that to a fracture property, which will be Kc or Jc, which will be a material fracture toughness that I measure in my lab. And you can combine both, and this is the idea of the transition flow size. I don't know how many of you have seen a graph like this in your fracture mechanics course. It's not taught all the time. Hands up if you have seen it before. Okay, a few people only. So this idea of the transition flow size is that if you have here I'm plotting basically applied stress versus crack size. So you can see that if you go back to Griffith or Irving, toughness, this is the relationship between K and sigma. So my failure stress will be Kc divided by square root of pi a, and maybe a geometry factor if there is. Let's assume geometry factor equal to 1. So things will fail, my applied stress will fail when Kc is when Kc divided by square root pi a equals to, when this sigma reaches this critical quantity. So basically, if I plot this, it looks something like this. You can see as I increase my crack, it's a inverse square root relationship. My graph, you can plot it later in MATLAB if you want, it looks something like this. So as I increase my crack size, my failure stress becomes very small. But of course, as we predict from fracture mechanics, if there's no crack, the stress will be infinite actually, right? So this grows quite significantly. And then the failure criterion for plasticity is just whenever my stress reaches a critical value, the yield stress, then plasticity happens. So that's independent of crack size, right? So that is basically a line, a horizontal line. And you can see that these two lines cross. Eventually you have a point where fracture mechanics is telling you that you're going to achieve failure at a higher stress than the stress at which you get the yielding stress. So this is what engineers call plastic collapse regime, and this is the fracture mechanics design regime. So you can equate these two quantities. You can say, you know the relationship between the stress intensity factor, the stress and the load, and the crack size. You make equal to sigma y, you make equal to Kc, and you compute the transition flow size for your material. And basically, you can see how it depends, right? So if you have a very tough material like a steel, your transition flow size is going to be large. If you have a brittle material like a glass, this guy is going to be very small. And this is quite important because it means that in a steel, if your crack is below this quantity, if my crack is somewhere here, things are going to fail by plasticity, are not going to fail by fracture. Engineers always want to work in that regime. These are basically strength-dominated failures or plastic collapse failures. You want things to fail due to plasticity because it's a much more progressive type of failure, because you can see with your own eyes that things are failing, you can replace your component. This is what engineers call fast fracture or catastrophic failure. You don't want these things from happening. So a lot of the engineering design goes about, I check my crack size, is it below this? I'm happy. Then I check my loads. Of course, maybe I want to have my load somewhere below this sigma yield. I'm going to be in this regime. That's fine. But this is a lot of the design goes into this transition flow size. And of course, if the transition flow size if your material is very brittle, this transition flow size is going to be very small, which means that in a ceramic, a small crack can trigger catastrophic failure. In a metal, my crack has to be much larger. And you can see here this Ashby plot of toughness versus strength. You can see here multiple materials and this transition flow size, how it changes from 100 millimeters to all the way to 10 to the minus 4 millimeters. So it can vary quite significantly. You can see here, by the way, how you have the toughest materials are engineering alloys, steels, nickel alloys. You can also find ceramics at the bottom here, some polymer foams, but cement, concrete, ice here, very low fracture toughness. And those here you can see the engineering ceramics. So relatively large square root meter, but then 10 megapascal square, 2, 3, 4, 5 megapascal square root meter, but also very low transition flow size. So little cracks are going to be problematic in brittle materials. More ductile materials lead to bigger cracks. By the way, you can also see here that in metals, there's a trade-off between ductility and toughness. So if I think of the steels here, look at this ellipsoid here. For steels, you can see that if I do something to increase my strength, I lower my toughness as well. Look at the shape of this. And this makes sense, right? What do we do to increase toughness in a metal? Or what do we do to increase strength? We want to put obstacles to plastic deformation. We want to, put whatever obstacle you think, carbides, whatever you think to increase your yield stress, to lower plastic deformation. And of course, plastic deformation also gives you toughening. The more plastic work, the more tougher your material is. So by putting obstacles to plastic deformation and increasing your yield strength, you are lowering your fracture toughness within this class of materials, steels. Okay, anyway, so this is the key point. This is one of the key points of fracture mechanics. You want to design to make sure that fracture does not happen. So for example, imagine they tell you have a plate with a crack of this size and this toughness, and what is the load that you need to work? So you say, okay, this is my crack size, I'm in the fracture regime, and I know the relationship between this. I have measured my fracture toughness, so I want to apply a load to my plate that is going to be around here, below the critical load. However, they say, okay, sometimes in engineering practice, you don't have full control over the loads. Imagine you're in a plane, and they say, okay, you're going to design this aircraft. We know what is the typical crack size, the typical defect that we can inspect in those components of your aircraft. And it's going to be subjected to an inside pressure of your plane. So you're going to be working somewhere here, and then you know what material to use, you know the pressure because you know fracture mechanics. But it could be that there's an increase in pressure that you didn't predict. So if you're somewhere here, maybe catastrophic failure will happen. So engineers will always try to work in this side of the picture. They want to make sure the cracks that you can find in your material are smaller than your transition flow size, to make sure that if things fail, they will fail due to yielding and they will not fail due to fracture mechanics. So that's the idea. Okay, that's all regarding linear elastic fracture mechanics. This is what we teach our undergrads in the first year, linear elastic fracture mechanics. But there's also plasticity, of course. So basically, most materials will have some sort of, we said stresses are infinite near a crack tip if you assume linear elastic fracture mechanics. So there will be some sort of non-linear deformation happening near crack tips for all materials. If we think of metals, you get plasticity, of course. The issue is that if this plasticity is very localized, linear elastic fracture mechanics, these ideas of K and J also apply. And you can see this here. This is what basically you have. Remember when you plot the stresses with this K field, you saw that the singularity was 1 divided by 2 pi r. So you have this square root type of singularity with r. If you look at r, it's 1 divided by the square root of r, right? So if you plot the stresses, if you plot the stresses ahead of the crack tip, you find something like this. So you find that when you have a plasticity, you have multiple regions. You have a large strain region, you have a J-dominated zone that I will explain in a minute, and then you have this K-dominated zone. And you can see that, if you plot your stresses as you approach the crack tip, you do have this K-dominated zone. You have the square root singularity. So still K uniquely characterizes your stress state ahead of the crack. You can still use K, you can still use linear elastic fracture mechanics. If you keep increasing your load, eventually your plastic zone starts growing, and then you have a region where J, the J integral, is valid. Some of you might have heard about this. It's kind of equivalent to G. It's a measure of, it was developed by Jim Rice at Harvard, or I guess he was at Brown at that time, and it's related to this singularity called the Hutchison-Rice-Rosengren singularity, the HRR system. But basically, again, you have a parameter similar to K that uniquely characterizes your stress state ahead of the crack tip. So this is the idea. You have a J, you have this singularity, and therefore you can apply the principle of similitude. You can use this idea to look into your small sample in your lab and the bridge, in the big bridge in the real application. So that's fine. And then if you eventually increase your load too much, then nothing is valid, and then no J, no K, all the parameters are needed. Yes?
Can I read the Y label next to log of?
Yeah, so this is sigma YY, so that will be the remote stress. So the stress ahead of the crack tip, not remote, sorry, the local stress ahead of the crack tip. And this will be R divided by some sort of sample size L. Yes. Yes, yes, it will be X ahead of. So you will see that basically if you plot this in a log, maybe show you here. This is, for example, the outcome of a finite element analysis, a DCB sample. So this is a sample with a crack like this. If you plot, you can do simple finite element analysis. You need to have a very fine mesh near your crack tip to resolve these singular stresses. But if you do that and you plot it log, you will see that if you start with a linear elastic material, initially you will get the K field, the singularity. If you plot the slope, it will be this kind of a square root. As you keep increasing your load, eventually you will only get this kind of HRR field, which depends on this is the strain hardening exponent, and then eventually you lose completely the whole thing. But you can see it if you plot, for example, just linear elastic material. You take a abacus console and you plot the stress field ahead of the crack with a very fine mesh. You will plot in a log plot the tensile stress or the opening stress versus the distance, and you will see that it follows that square root singularity. Yeah, this is an example of a paper that we have in the submission where you basically do these calculations. This is J, the measure of the applied load. You can see that as it increases, initially you get this singularity of linear elasticity. So here K is valid, here J is valid, and eventually, nothing is valid because you have a lot of plasticity. That's the idea. The last thing I want to say, and then we'll do a break. Let me see. I have a few more things. I'll continue a bit more now. So the last thing I want to say, or one of the last things I want to say is that, okay, what do engineers do when you have plasticity then? How do we account for these K, J, and so on? Normally they use what we call failure assessment diagrams. So here you plot the fracture ratio, which is called KR, which is basically a ratio between K and KC. So when this is equal to 1 is the linear elastic fracture mechanics. And then versus the load ratio, which is a measure of the load versus the plastic collapse load, the load that will cause the yielding of the component. And then they eventually, there's various ways of building this kind of failure assessment curve or first measurement line. But at the end of the day, what you want to count is that for the fact that basically you want to go from here to something that you can also use. This you can also use for elastoplastic fracture mechanics design. But they do something like this where basically here I'm going to the extremes. I'm taking this stream, the plastic collapse stream, and the linear elastic fracture mechanics stream. But in reality, things will go from here to something like this, more progressively. So this is what a failure assessment diagram captures. So first you can plot the linear elastic fracture mechanics one. The linear elastic fracture mechanics just tells me at a critical load, failure will happen. So that's one line. The plastic collapse will be as well. When P equals Py, that's what you get. And then how do you go from this line to this line? Basically, there's various ways that you can do that. It's all based on this concept of J. J can be related to the stress intensity factor. So you could define some sort of effective stress intensity factor that will give you like an elastoplastic stress intensity factor based on this J integral. Because remember, there's a region where K is not anymore valid, but J is still valid. And when you take that, there's multiple approaches in the standards. Engineering standards have multiple approaches, but they all look something like this. So depending on your yield stress and your yield strain, you get a curve that looks something like this. Then it's basically a way of going from linear elastic fracture mechanics, K equals Kc, plastic collapse, the load equals the critical load, and then something in between that is based on this J integral, or an effective elastoplastic fracture driving force. That's the idea. Okay, so now at this point, you may wonder, how can it be that components fail? If fracture mechanics is there, and components fail all the time everywhere, in very well-developed countries where fracture mechanics standards have been established for decades, where engineers have well understood safety factors, where they follow protocols to the line. This for example happened in Italy a few years ago. This was in the US, the biggest environmental disaster not that long ago. So why do things fail if we understand very well? We have this transition flow size. We said, if I look at my crack, if my crack is bigger than this, I just need to make sure that my load is below the fracture critical load. If my crack is a little more than this, then for plastic collapse to occur, I just need to make sure that my stresses are below the yield stress. Why do things continue to fail? Well, one thing is that, of course, there's other things that go beyond fracture mechanics. One of them is fatigue. Basically, this transition flow size is being reduced. And this transition flow size can be reduced due to fatigue. It could be that, because we are applying cyclic load, we are basically changing your material. We think that we understand this toughness, but in reality, this toughness is changing because fatigue is degrading that toughness. And the other aspect is that we think that we understand this toughness, but the environment, for example, in this case, was corrosion. The environment is changing my material. So some things are happening. I think I understand my material, but the material I'm thinking of, the material I tested in my lab, is not the material that I'm seeing in reality, because maybe it underwent cyclic loading, and so fatigue has changed my transition flow size, or environmental degradation. So one of these sources of degradation is, of course, fatigue. Most engineering components are subjected to cycle loading, and I would say 90% of failures today are related to either environmental or fatigue factors. What happens is that, of course, you're applying a load that is supposed to be safe, but because you apply that load millions and millions of times, you are actually doing small degradation of your material, and you actually damage your material. It's not enough to grow a crack, but eventually, after applying a lot of load, the crack does indeed grow. And typical application and fatigue quantities that will make use of it are, if we think of as a cyclic load, it will look something like this. It's the simplest one you can think, a sinusoidal cyclic load. So you have a minimum stress and a maximum stress, and then you have a stress range or stress amplitude. This divided by 2. So this is one cycle, right? If I go from here all the way to here, this is one full cycle. So there's such a thing as a number of cycles to failure. Here we'll have 1, 2, 3, 4, 5. Then eventually you have a critical quantity, number of cycles to failure. So you do tests under cyclic loading, and eventually you reach a certain number of cycles, you see failure. Those cycles that loading cycles will be characterized by the applied stress, of course, this stress range, the mean stress, and the stress ratio, which is the minimum divided by the maximum. So these are the critical quantities that you'll see in all this fatigue analysis. And when we deal with fatigue crack growth, we deal with this cyclic, the stress intensity range, and this crack growth rate. And I see that I'm exceeding a little bit the time of the coffee break, but I think I'm going to continue because I only have a few slides left, and we can start a bit later. So that's the idea. You have a minimum stress, you have a maximum stress, you have a stress amplitude, a stress range, you have a mean stress. Mean stress matters, of course. You could have the same stress range with different mean stresses, and as you can imagine, the larger your mean stress, the more damage you're accumulating there. Stress ratio also matters. And then when we talk about cracking, when we talk about fatigue crack growth, we talk about the cyclic stress intensity range, which is the same ideas as before. We had before K equals Y sigma square root pi A. Now it's delta K, the stress intensity factor range or amplitude, multiplying the applied load, which is now cyclic. And then we also have a measure that we call crack growth rate, which is dAdN. That tells me how fast my crack is growing as a number of cycles. That's the idea. So basically in fatigue, let me see, I think I have a few slides more only now, and we'll do the coffee break. So in fatigue, we basically have two approaches, or two big regimes, or three maybe. So you can see here, what we call regime 1 or A, regime 2 or B, regime 3 or C. Regime A, by the way, I'm plotting here the log, this is the stress intensity factor range, and this is the dAdN, so this is the crack speed, the crack growth per cycle. And remember here, even if I apply a constant load, my delta K is going to change as my crack grows, because even if this guy is constant, my crack size is increasing. So normally in a fatigue crack growth experiment, your applied load will vary between the same sigma min and sigma max, but your delta K is changing because your crack is growing. So you have these regimes basically. At a very low applied, the load is always the same, but the crack is small, very small cracks. You have this regime A where you nucleate a crack. And this is the most complicated one because it's very macrostructurally dominated. So there's lots of material science in there. You need to deal with the nucleation of a crack. And that's, again, too complicated. And if you have a material that is very clean, where you have almost no defects, remember there's always defects, but they could be very, very small or almost non-existent. If you have defects that are tiny, then you spend a lot of time nucleating that crack. Most of the fatigue life, 90% of it. Then once that crack has grown into a millimeter crack, a macroscopic crack, you enter this Paris law regime, which is what we call the defect tolerance regime. There the crack grows according to this expression. And I don't know if you know the story of the Paris law, so how many of you have heard about Paris law? Okay, more than before, that's good. Yeah, but I don't know if you know the background to it. So Paris was an academic who passed away some years ago. He was based in, I think, University of Washington in St. Louis. And I think Boeing had a program where you could spend a year working in Boeing. Academics could spend a year working in Boeing for them to get exposure to industrial problems. And then when he was working in Boeing, he realized that all the fatigue data they had fitted a law that looked like this. And then he tried to publish a paper out of it, and all the journals turned him down because they said, well, I mean, where is the physics in there? It seems like a bit out of the blue. You say all the data fits this curve, this expression, but okay, what is, so DADN is, okay, crack growth versus, number of cycles. K is a stress intensity factor, so there is some sort of fracture mechanics principles in there, but what are C and M? These seem like fitting parameters, out of the blue, there's no mechanistic understanding. Even though it includes some fracture mechanics, it was thought to be a bit too empirical. So it was rejected by all journals. Eventually he published, I think, in the local journal of the university, but eventually became, of course, a very well-cited and famous paper, and Paris died being a very famous person, because the data, everything was fitted very nicely by this equation. And you will see later that, there's a meaning to it. There's a physical understanding of it. But basically you say, everything relies on two parameters, M and C. M for metals is between 2 and 4, and then C depends on the material. But this is a regime where you can fit your data, and then eventually is the final regime where your crack approaches your critical crack size that we discussed before. Then you accelerate your crack growth, and then you get an unstable fracture. That's the idea. So there's two approaches to fatigue, for example. One is what they call total life approaches. This is the industry that, now I'm going to say maybe they know a bit less about fatigue. Maybe they want to take less risks. So the industry that will just deal with crack initiation. This is a more conservative approach. They'll say, okay, I'll do some testing. I'll figure out I'll do some SN curves, basically, uniaxial cyclic load. I'll see when things fail, and I will worry only about regime A. Because when you measure with this uniaxial tension, it's mostly regime A. It's not a fracture test. So then I will just worry about total life. So I'll say, the moment I nucleate a crack, I'm going to replace my component, and that's the end of it. This is the total life approach. The other approach is the one used by, for example, the aviation industry, the defect-tolerant approach. It requires understanding fracture mechanics. It requires more inspections. But if you were to do a total life approach, in aviation, flying will be very, very, very expensive. Every time you had to replace a crack in an aircraft component, it will be very, very, very expensive to fly. So what they do is they say, okay, I know I have a crack, but I know what speed my crack is going to grow because I did a test and I know my C and my M for my material. So I'm just going to do inspections and check how fast my crack is growing to make sure that I never get to this point. So somewhere here, I basically replace my component, but I don't replace it here because otherwise it will be too expensive. So this is the more sophisticated industries. This is what we call defect-tolerant approaches. So it's more based on fracture mechanics. You do inspections. You determine how many cycles it's going to take for that crack of a given inspected size to reach a critical quantity, and then you replace your component before failure happens. And then, of course, in between, you do various inspections to make sure that you're not deviating from what you thought. So let's look first at the first approach, these total life approaches. How do we normally come up with these total life approaches? Well, very simple. We do uniaxial tension tests. So this is what we call the SN curve. Many of you will be familiar with this. You have a bar. You load it on the cyclic loading at a given stress amplitude or range. And when it fails, you get a point. You count the number of cycles it took to fail, you get a point. Now you do another experiment with same bar, same material, but you apply a different stress range, you get another point. Again, and again. You're just basically changing the load and measuring the number of cycles to failure. Eventually you get enough points that you can draw a line, and this is your SN curve. You can use this curve to design. And SN curves look a little bit like this. This is stress amplitude again versus cycles to failure. This is for a given steel, for an aluminum alloy. And you can see a few things here. First, we're dealing with uncracked smooth samples. This is not a fracture test by any means. So mostly we deal with crack initiation. We try to use samples that are as smooth as possible. So mostly we spend most of the time nucleating a crack. There's a lot of scatter in the data. Remember, similar to what we discussed at the beginning, the strength is very defect sensitive. The same goes for this kind of SN curves. You can see here, this is real data. This is a log plot. You span almost 1-2 orders of magnitude for samples that should be identical. All these crosses should be in the same spot. They're samples of the same material subjected to the same load. They should all be in the same spot, and they're not. So there's a lot of scatter because they're very even though we think all are the same, they have different defect sizes to start with, and it's very microstructurally dominated. So there's a lot of scatter in the data, and of course results depend on the R ratio, environmental conditions. And then the other thing you need to take into account is that you may have or not a fatigue threshold. So whenever you see in an SN curve this arrow, this means that the sample did not fail. They don't want to be doing a test for years, so eventually how long a test takes, of course, depends on the frequency that you load, but eventually no matter what frequency you apply, it's going to take a long time. So they do tests until a certain point, and then they say, we stop. It didn't fail at this point, it's likely not going to fail. So some materials do show that, they experience what we call a threshold or an endurance limit. Other materials like aluminum alloys do not. And a lot of people use that to design, right? So they say, okay, this steel is going to have an endurance limit of this load, so I'm just going to remain below this load, and then I'll be safe. And then one has to, of course, be careful as well. This is uniaxial, 1D. In reality, stress components have a stress razor, so you have to do a finite element analysis. You get your stress, and then you even though your applied load might be here, your stress razor might take you here, so you go and test what is the effect of stress razor. And the last slide that I have before the coffee break, of course, we also deal with fatigue crack growth. So this is the total life approach, mostly dealing with crack initiation, which is arguably the most or the least understood part of fatigue. It's very macrostructure dominated, more complicated, more maybe scientifically exciting, so to say. The fatigue crack growth part we know more or less. This still remains a bit empirical, but Paris law does describe the data quite well. You can see some examples here. So basically the idea is that you calculate your stress intensity factor range. You know this relationship based on Paris law. You know your M and your A from test data. You can get it from here. And therefore you just need to integrate that expression and calculate the number of cycles into your crack reaches this critical crack size where cracking will be unstable. So you know fatigue crack growth is a stable process. Your crack is growing slowly. You take a snapshot. You see my crack is this size. My applied load is this. That will give me K. I know my variation in K. Then I know how quick my crack is going to grow if I have experimental data for that material, a fatigue crack growth test, and then I just measure how the crack grows. Okay, that's all for the first part. Any questions so far? Yes?
The Paris law is really interesting. So in the engineering structures, how do they know which stage of the crack in there?
Did I include? Sorry, I didn't include any appendix slides, but I have some examples that we normally use for our students to put it into practice. I didn't have time to do examples with Paris law, and I suspect that some of you have seen that before, so I didn't want to. But yeah, this is a good question. So, for example, in aviation, they will tell you how they work. For example, in aviation, they will say, imagine you have a crack in the wing, and say, okay, we saw this. We have an inspection regime, so from time to time we inspect our wings. Every time, let's say every 5 flights, we go and check your wing, and we identify a crack size. And these inspection techniques, they'll have a resolution. They cannot see very tiny cracks. They can see cracks. Normally they use these non-destructive evaluation techniques. They will see cracks of typically 1 millimeter or so, or larger. So they will do an inspection regime, and they'll say, okay, we have a crack of 1 millimeter. We figure out that we have a crack of 1 millimeter. And even if they don't see anything, because their non-destructive technique cannot see below 1 millimeter, they will always assume a crack already exists and it's 1 millimeter. Because if you had a crack of 0.99999 millimeter, the thing will not see it and the crack will be there. So they say, we start with a crack of 1 millimeter. So you go here, you can integrate this. So dN goes here, dA is here, you integrate, and you integrate a crack over 1 millimeter to whatever is the critical crack size. The critical crack size will be given by static fracture mechanics. So here, from your toughness of the material, you know that whenever you reach, or maybe even simpler, right? Here, if I know my toughness and I know let's say that aircraft wing we know is going to be exposed to a pressure of, maybe if we think of an aircraft component in the inside of the plane, basically every time you fly, you increase the pressure, you down the pressure. So it's a pressure of whatever, 400 megapascals, whatever it is. Then you can solve for your critical crack size depending on the toughness of your material. You know the toughness, you did an experiment. So let's say that your critical crack size of this metal, an aluminum component that you use might be 6 millimeters. Okay, so you have 1 millimeter to start with, and when it reaches 6, it will crack. Normally they won't wait until it's 6. They will do 5, or they'll put some sort of safety factor. So then they will do some fatigue crack growth experiment, like this one. This is in the lab. That will give them, they will feed the data, and that will give them the A and the M. So then you integrate. You bring dN to the right side. You bring d8 here. So you integrate from A going from 1 millimeter, the crack that you already have, to 5 millimeters, the one that will tell you, okay, you need to replace the component when you reach 5 millimeters. And then on the right side, you integrate over this. So this is a quantity. It could be a 4. This could be whatever other number it is. Delta K, this is delta K. This is the load. You said the pressure was going between 0 and 400 every time you did a cycle. This is the Y and the crack size. The crack size will have to go here. And then you integrate between number of cycles, which could be from 0, the starting point, to N, which is the number, what you're interested in, basically. So you want to know after how many cycles will it take my crack to go from 1 to 5 millimeters. So yeah, the A, the square root goes here, the A goes this way. You put everything related to A on one side, number of cycles. You have everything. The only thing that you're missing in this integral is this number of cycles at which your crack becomes 5 millimeters. So you basically solve that integral, and then basically you put in the numbers, and you end up with saying, after 3,400 cycles, you get a crack size of 5 millimeters. So they will say, we get 2 cycles of load every time we fly, because it's one to go up and then down. So that will mean after 2,000 flights, let's go and check my crack, how it is. And we expect that we will have to change it every 2,000 flights. And maybe they don't inspect every 2,000, they inspect every 500, just to make sure that things are fitting the way, and then they'll replace the component. That's more or less how it works. Yeah. You know your crack speed because you did an experiment. You know the initial crack size because you have some techniques that you do inspections, and you just show that your crack is growing at that speed. And then you know your critical size from fracture mechanics you replace before you reach that critical size. Okay? Any other questions? If not, I suggest we do a break. So roughly half an hour. So let's say 11:15, we are back here. Perfect.